morning, everybody. Thank you for joining us. In about 2006, when ARM first released their initial Cortex-M processor, they also started work on a standard called CMSIS, the Cortex Microcontroller Software Interface Standard. And this is a series of standards that intend to support development of C code on small Cortex-M based microcontrollers. They've recently released CMCs version 5, which now provides some expanded functionality to support the Cortex-M7 and also the new ARMv8-M processors, which will start to emerge probably earlier next year. So I'd like to spend a little bit of time just looking through some of the additions that have been added to CMSIS to support these devices. The CMC specifications allow us to combine software so that it can be distributed in a software pack. So these are device family packs or middleware support packs. So this system is currently or has been unique to the Keil-MDK-ARM development toolchain. However, there's now a plugin for Eclipse that allows the software packs to work with open source tools as well. So now the CMC standard is supported in multiple tool chains and the packs are designed to work with the key compilers, the commercial compilers, which are Keil, the ARM compiler, IAR, and also the open source GCC. So this allows a wide range of support to easily be adopted by a number of tool chains, both the commercial Keil tool chain, but a number of open source Eclipse-based tool chains as well. The latest version of CMSIS, which is version 5, was released probably about a couple of weeks back now, and there have been a number of additions to the CMSIS standards. So in the CMSIS core specification, so this is the low-level drivers that or low-level functions that code can use to talk to the key processor registers. So here these have been expanded to support the Cortex-M7, particularly its cache management, and also to support Trustzone within the ARMv8-M processors as well. There's also a standardized API for small footprint operating systems called CMCsArtists, and the latest version of CMSIS releases version 2 of this API, which has been expanded to support some new functionality and also supports the ARMv8-M processors as well. So within the Cortex-M7, this retains the programmer's model that we're used to within the other Cortex processors, but it introduces a more of a memory hierarchy. So it has tightly coupled memory regions which allow you zero wait state access to code and data. But it also has a couple of on-chip caches, an instruction cache and a data cache. These are configured through the memory protection unit, so we can say what regions of memory are covered by the caches, and we can also set up their cache policies as well. So for example, the data cache can have write through or write back policy. So this may cause data coherency problems in a larger system where we have other bus masters, typically DMA units. So the data cache can shadow the underlying SRAM memory. So there's a coherency problem between the various DMA units and the CPU core. So within the CMSIS core specification, we have some low-level functions that allow us to enable the caches. So with the instruction cache, generally once this is enabled, we can just let it run. And it's kind of self-managing as it executes. However, the data cache we may need to provide additional support for, depending on the way that we've configured the cache policy. So here we can enable and disable it, but we also have functions where we can invalidate the cache, that is, flush the cache and reload from the system memory, or clean the cache where we write the cache data out to the system memory. So this can be done as a cache-wide call, or we can also invalidate or clean data by region address and size as well. So managing the cache becomes a lot easier with these high-level functions. With the ARMv8-M processors, we now have the introduction of Trustzone, which creates a processor that effectively has two states that it runs in, a secure mode and a non-secure mode. So the secure mode is kind of like a container within the processor that has its own region of RAM and peripherals, however we want to configure it, and those peripherals and RAM and code can't be seen by code that's running in the non-secure state. So you can kind of think of it as a sort of firewall within the processor. So in practice, this means that we double up on a number of processor registers. So we have separate stack pointers for the non-secure and secure mode. We also have an additional secure memory protection unit, SysTick, system control unit, and a new unit called the secure arbitration unit, attribute unit, sorry. So within CMSIS core, we have a number of functions which have been adapted to support the Trustzone within ARMv8. So in terms of the existing core register functions, the NVIC access functions and SysTick, these essentially provide additional functions that allow us to access the non-secure registers when we're running in secure mode. So typically when the processor starts, it will boot in secure mode, and we need to configure the secure registers and also the non-secure registers. So these new functions allow us to easily do that. Then we have some new functions to configure the system attribution unit or attribute unit, and also to manage the RTOS as it switches between secure and non-secure mode as well. So in terms of the system attribute unit, there are only really three functions, a setup, enable and disable, and the programming model for the system attribute unit is very similar to the memory protection unit. So you have a few registers where we're programming up regions and saying whether these regions are secure or non-secure mode. So when we run the setup code, this accesses some arrays that are configured in a header file called the system partition header file. So this is an extension to the existing CMSIS functions. So we have our startup function, which is a standardized interrupt vector table. When we leave the reset vector, we then enter the system init code, which goes through to configure the key system peripheral. So currently, typically things like external bus or oscillator clocks. So now the system init code has been extended so that we can configure the ARMv8 system attribution unit. So to configure that unit, we now have this new header file called the partitions header file. And within this file, this is a templated file, so we can view it either as C code or as just a drop-down list. And this is split into a number of regions. So we can set up each of our 8 regions. We can specify the start end address and whether this is a secure code or non-secure region. We can also specify the sleep behavior. So when the device goes into sleep, we can say whether it's enabled by secure or non-secure peripherals. And we can also route interrupts between the two interrupt units that are now on the ARMv8-M device, so the secure nested vector interrupt controller or the non-secure NVIC. So again, we can decide which peripheral is going to execute an interrupt in secure state or non-secure state. And then finally, depending on the manufacturer, we may have multiple SysTick units, so we can also control the behavior of the SysTick through the system partition header file as well. So this makes setting up the Trustzone configuration very straightforward, and it's all carried out by the system startup code, so that as soon as we enter, we're running with a configured processor ready to start executing our code. The toolchain have also been modified so that we can create a multi-project workspace. So typically we'll have one project that's designed to build the secure code and a separate project that's designed to build the non-secure code. And then the compiler tool generates a small library function which handles the symbols for jumping between the two projects. So again, linking secure and non-secure code is largely handled by the toolchain. And we can decide what model the processor is running in the global options for target, and here we can simply select secure or non-secure mode. Also, the compiler has support to generate execute-only code. So if you're running off of external flash, we can put all of our code constants and literals in there and not have to use any data accesses to pull that information out of the memory. So again, this makes it a little bit harder for hackers to attack our device over a network and start poking around at crucial bits of memory. Now, when an ARMv8 processor starts, it will boot in the secure state. As I've mentioned, the startup code will configure the security attribution unit. Once that's configured, we can pass execution to the non-secure code, and then in a simple model, our code runs in non-secure state, making calls into the secure code, which again, it can access any function that's been marked as an entry point with a secure gateway instruction. So we can then easily link the two projects together to make calls from non-secure into secure state. However, if we're using a small footprint operating system, we will typically have our RTOS started and running in non-secure state, but we'll need to make calls to threads running in secure state. So there is another set of functions that handle a context switch between secure and non-secure state, and these can be implemented, but these can be used by anybody designing a small footprint operating system. Again, this is the sort of code that anybody could write. However, the CMSIS RTOS functions provide a standardized way for small footprint operating systems to manage a context switch. So any operating system that uses this will allow middleware or other bits of code to be accessed through this standard interface. So it's quite important when we're trying to mix and match third-party code. With the release of CMSIS version 5, there's a new version of CMCsArtists has been released, and this brings a significant number of new features. The previous version of CMCsArtists always used static memory allocation for all of the objects. It's now possible to have a dynamic memory pool where we can create threads or operating system objects and destroy them at runtime, and they'll be dynamically allocated and deallocated in this memory pool. As I mentioned, CMCsArtists version 2 supports the ARMv8-M architecture, and it also provides messaging provisions for multi-core systems that are starting to emerge. So where we have a microcontroller with multiple Cortex-M cores, or a device with a Cortex-A and a Cortex-M core. The version 2 of the RTOS API also supports C++ runtime environments, and the C interface is now complies to the ARM binary interface, so it allows different bits of middleware that have been built with different compilers to easily work together in an operating system environment as well. So in the RTOS, we can RTOS version 2, we can create one global memory pool, so then all of our operating system objects will be allocated into this region of memory, so we can create and destroy and reuse that memory. We can create also object-specific memory pools, so pools dedicated to threads or semaphores or messaging, and those are then managed so we can create and destroy things on the fly. Or if we were writing for high integrity or safety critical applications, we can stay with the original static object memory where everything's allocated at compile time. So it's more deterministic and we can verify it. So this leads to a slightly more complicated configuration file. So here we can allocate a global memory buffer where all of our objects will be placed, or we can create object-specific memory regions as well, where specific objects will be created. Then when we create threads, we can say whether they're static, dynamic, or they want to go into the object-specific memory region. The API of CMCsArtists 2 has also been extended. It carries over much of the same functionality, but it provides better visibility into many of the operating system objects. So for example, in a message queue, we can get the capacity of the message queue, we can see the message size, we can get the count of messages that are in the queue already. So similarly for semaphores, memory pools, we just have more API calls where we can interrogate and see how that object is behaving at runtime. There is some renaming of functions as well. So for example, here we have a typical API call where we're creating a new thread. So in the previous API call it was OS thread create. This has simply been changed to OS thread new. And here we're passing in the C function, an argument that we may want to pass at startup. But the major difference is that the parameters of the thread are now configured by passing a structure which defines all of the key parameters for the object that we're creating. So in the case of the thread, we're giving it a symbolic name for debug. We can pass some binary attributes. If we're using object-specific memory, we can pass it memory to create its control block, its stack size. We also pass it the initial priority that will be created with as well. And if we're working with ARMv8, we can tell it if it's a thread that's going to run in secure or non-secure mode. So we can give it its Trustzone ID as well. So, and again, many of the other operating system objects follow a similar style of creation with this new API structure. There's one new object within the CMCsArtists 2. In CMCsArtists 1 we had signal flags which were created alongside each thread, and a thread could halt and inspect its signal flags. When a particular pattern was set, it would start executing. Those signals are still present, but there's a new object called event flags, which can be created as a global object, and individual threads can wait for patterns to be set on this object. So multiple threads can now wait to be signaled by one group of flags. and then any thread can access that global object and set or clear flags. So now we have a global synchronizing object which can be used to synchronize multiple threads. There have been also some RTOS calls that have been deprecated. So the mail queue that was used to send formatted messages between two threads has been removed from the API. And this has been or can be replaced by using a message queue which sends a pipe of objects and memory pools. So we can create a memory pool which allows us to store formatted data, and then we post pointers into the message queue to the particular memory pool block that of data that we want to pass to another thread. So this is a very efficient way of transferring data between two different threads. It's a zero copy mail queue, so we're only moving a pointer rather than piping large blocks of data between two threads. The message queue itself, the API there has been extended, and it's also now possible to prioritize messages. So before, a message queue was a simple FIFO where we could post a message and they'd be received in order at the destination thread. Now we can set a priority, so we can post general messages, and then we can post a high priority message which will immediately jump to the front of the queue. The message queue before had a width of 4 bytes. It's now possible to extend that to a user-defined size. So if we want to, we can post arrays of data in a message queue as well. Although that's not as efficient as using the memory pool and message queue as described above. If you're already using CMCsArtists 1, it will be necessary to move to CMCsArtists 2. The Artists 1 will be supported probably for a significant period of time, and however it will eventually fade away. So it will be necessary to port your code over to the new API. Currently there is a translation layer that's provided so that we can mix version 1 and version 2 API calls and then migrate your code over time. And there is a migration guide and a list of deprecated API calls that's provided within the CMCsArtists 2 documentation as well. So while this is necessary work, it should be a fairly easy translation to do. As CMCsArtists 2 is intended to be a standardized API, there are a number of operating systems that support it. So there's also a validation pack that can be downloaded into your toolchain, and this allows us to exercise all of the key features of the operating system to check that this implementation of CMCsArtists is actually accurate and functioning as it should do. Currently, this is only available for RTOS version 1, but will be extended to support RTOS version 2 in the near future, but we don't have a release date for that quite yet. If you want to try out some of these examples and have a look at Trustzone, if you go into the MDK-ARM pack installer and select Devices and ARM, and in the Examples tab there are a number of ARMv8-M examples that run in simulation, so it's possible to build these and experiment with them. There's also a number of examples for RTOS v2 as well, and currently working on transferring our training examples from RTOS v1 to v2. If you'd like a copy of these for reference, raise that as a question and I'll send them out to you at the end of the webinar, or when I have them ready, more likely. In terms of the MDK-ARM development tool, this has also been expanded to support particularly ARMv8-M, so it's ready for new processors when available. So currently, as we saw, the tool IDE has been architected to support, to provide support for Trustzone. It already includes the ARM compiler 6, which is necessary to generate the additional instructions to support ARMv8, the ARMv8 architecture. So currently this is a bit of a beta release, but it's there and functional, and it's being optimized so that it should be ready in time when the actual hardware arrives. So at the moment, if you're developing for the current Cortex-M processors, we'd recommend staying with the ARMv5 compiler and then move over to the compiler version 6, probably in the Q1, Q2 next year. There's some interesting new debug features built into MDK-ARM as well. So there's a new component viewer that supports both the RTOS v2 and also the ARM, the Keil middleware libraries. So this can be opened under the View Watch windows, and then you have additional selections depending on the RTOS or middleware that you're using. So this shows all of the key variables or constants that are within the middleware in real time as you run the debugger. So it provides very good visualization of how the RTOS or the middleware component is running. These files are loaded automatically when you're using the Keil middleware, but this is an open standard, so it's possible to import third-party component description files into the toolchain, and it's also possible to design your own as well. So if you're working with a project over a long period of time, you can display key symbols, key structures of your code in a component viewer window. And it's really a matter of writing an XML file that describes the symbols that you want to look at and then describes the layout of the window. So this is sort of a morning's work or a day's work tops. There's also a new feature called the event recorder. So here, as our middleware code runs, there is the debug library has been instrumented so that it writes into a small region of memory, like a trace buffer, and then the debugger can download this this information and display it in the event viewer as an application trace. So here we get a timestamp, we can see the component which has generated the message, the actual message, and then any values that are being transferred. So again, this gives us a very good runtime view of what our middleware is doing. As I say, this is intrusive in that the debug library is doing some extra writes and we're using some memory on the processor, but the upload into the debugger is done through the core site debug architecture, so this is non-intrusive. In the past, this kind of debug was done through the instrumentation trace, but this had a problem that the instrumentation trace was not available on Cortex-M0, M0+, whereas this event viewer method will work with all Cortex processors. So it extends this runtime diagnostics to any Cortex processor. And you can add these messages into your own code. So within the runtime environment, in the compiler section, we can tick the box to enable the event recorder. Then we can simply include the event recorder header file, initialize the event recorder, and then we have a number of functions that allow us to transfer strings or binary messages up to the event recorder. So again, as you write your code, you can add this instrumentation, and then when you're debugging in real time, you can get an application trace on any Cortex processor. And if you add these as you're developing your code, it becomes increasingly valuable as the code gets more complex and you need to track down or verify runtime deadlines or bugs and see what's actually happening to your code as it executes. It becomes a very powerful debugging technique. The ARM have also released their Embed OS system, which is an Internet of Things system. This is an open source code that allows you to put a client on a Cortex processor. This talks to the CoAP protocol up to some servers run by ARM to transfer data up and down to the small ARM device, and then that data can be accessed through standard REST API through a web application. Now this is open source and it will build with a number of tools, but it has now been added as a client within the MDK Pro. So here we can add the Embed Clients, the minor scheduler and the Embed TLS Security pack to our code, and then we have templates that will add the necessary code to start and allow us to transfer data to and from the ARM servers. So this becomes very easy to implement within the ARM MDK Pro. The ARM Embed, we're also working on a small open source project, which is the Embed OS Browser, which hopefully will be available early next year. So this is a desktop browser that will talk to the ARM servers, the ARM connector, Embed connector, and allow us to view all of our nodes, look through the endpoints within those nodes, view the current data, and also view large blocks of data as well. So again, this is a simple tool that allows you better visibility of what your Embed client is doing during development, and can also be used to monitor a network during deployment as well. As I say, that will be available under an Apache open source license, hopefully the early part of next year. The Embed TLS Security pack that's being used, that's freely available to use, is also being used by Keil to implement TLS security for their network stack as well. So at the moment we have a secure web server, and then secure versions of the other application layer services will also be released over the coming year. Just to finish off, one thing that a new tool chain has also been added to the MDK Pro. This is the new DS-MDK. So this is an Eclipse-based toolchain that provides support for Cortex-A devices. Initially, this is the IMX6 and IMX7. So if you have an MDK Pro license, you can simply download this toolchain, license it, and then work with these devices. Within the DS-MDK, it imports all of the CMCSIS packs, so it can be used to develop for Cortex-M devices as well. So it's not really there yet to work with standard microcontrollers, but it's really aimed at working with heterogeneous devices, so where we have a Cortex-A processor that will typically be running a feature-rich operating system like Linux, and a device that also contains a Cortex-M processor, typically a Cortex-M4. So on devices like IMX7, I think we have a Cortex-A7 and also a Cortex-M4. So we can run, say, Linux and then a real-time operating system on M4. So this increases our overall complexity. So we then have the two operating systems, and then we have to manage communication between them through shared memory. And the DS-MDK is a tool chain that's designed to try and make that process as easy as possible. It also works with the Ulink Pro. So again, if you're using Ulink Pro on Cortex-M, with the DS-MDK, it can be used to do bare metal debug for Cortex-A devices and also Cortex-M. If you have Linux running on the Cortex-A, we can also connect to GDB and run an application layer debug within the DS-MDK debugger as well. There is a getting started guide which gives you an introduction to DS-MDK using both the NXP Sabre board and also the Hitex single board computers for IMX6 and IMX7. So it's, again, we're building up experience with this, and we'll cover this in more detail in a later webinar as well. So again, if you are planning to work with Cortex-A in the near future, then DS-MDK gives you bare metal support for M and A, Linux application debug, and also introduces all of the CMSIS support that's currently available for Cortex-M. So I'd like to thank you for attending today.